Thank you for joining this session. The title of this talk is about Texera, the system our team has been building for the last few years. I would like to make the webinar more interactive, so feel free to ask questions during the presentation. Also, we decided to show a live demo in the process, which is more fun, more exciting, and also more challenging. So let's see how it goes. So I would like to start the presentation by considering example scenario, which is typical in sequence analysis in biology. So in this setting, let's assume we have a lab at some university. In the lab, there's a PI, Professor Alice. She is a biologist, and in her lab, she has a few staff members, students, postdocs, and we call them bioinformaticians. So here we have two bioinformaticians. One is Sally, one is Bob, and they do all kinds of analysis related to sequence data. And I'm going to pretend to be Sally for the presentation. So this is a typical pipeline. Many bioinformaticians conduct their research related to sequence data. And they should capture most of the use cases. And so let me go through them very briefly. I'm pretty sure many people in this audience, they are more familiar with the details about each step. Yet for the sake of this presentation, let's go through the steps quickly. So the first step, the input of the whole pipeline is some FASTQ sequence data, some read data, could be a large amount, easily in a scale of gigabytes of data. And then it goes through first step. Here I use Cell Ranger as example, but there are also other solutions like Star Solo as example. But for the running example, let's use Cell Ranger just to show the step, which will do some processing of the read data and produce a count matrix. And this count matrix will go through several steps. Step 2 is to do some quality control. We can remove some low quality cells based on some criteria. And then we'll do some normalization, step 3. And in step 4, we reduce the dimensionality. And in step 5, we're going to integrate the data from different data sets provided by different donors. And in step 6, for the integrated data, we can do some clustering using one of your favorite clustering algorithms like K-means. And then we do, once we generate the clusters, we can do some annotation on the clusters and eventually produce something like a UMAP for deep analysis. So after step seven, there are more steps I'm not showing here, but on this slide, I just show some examples. Many of the analyses could be related to the AI ML analysis. So this is a typical pipeline. So let's think about Sally's life. Sally is a bioinformatician. She writes code. Here I show some of her code. You do not need to understand the detail, but I hope you get some sense about what she's been working on. Here I just show kind of a main 3 steps. They are doing data preparation, later data analytics, and then later visualization. So this is the job of Sally. So there are a few challenges Sally faces when she does this kind of coding. First of all, coding is really hard. Even though there are many very smart bioinformaticians, understanding code, managing the code, and sharing the code is extremely challenging. The second one is very often this kind of code, they rely on libraries in different languages, in R, in Python, and these libraries keep changing. They have different versions. So it is very critical to make sure your code, your program is using the right versions of the right libraries, but keeping track of the right versions of the libraries itself can be time consuming. The third thing is to run this kind of computation, Sally needs some computing servers. In most cases, they rely on staff members of that university who maintain some servers, and then Sally can remotely log into that server and do some computation. And in many cases, the server might be shared with other collaborators from same lab or possibly from the same campus. A big main pain point for many bioinformaticians is the scale. Here, we all know the data keeps increasing. We're dealing with gigabytes of data, even terabytes of data, and some of the computation steps can easily take hours, days, or even weeks. And you can imagine how painful that process can be. And sometimes after you run the job for like a few days, the program crashed, and all the previous computation is gone, and the computing resources is also wasted. One more thing, even though in the current setting, I assume the PI Alice has two bioinformaticians, and she's lucky because she has the resources, she has the funding to hire these talented bioinformaticians to do this kind of analysis. And there are many also labs that have limited resources. They couldn't even afford hiring this kind of bioinformaticians. As a consequence, they don't have this kind of skills or manpower to do coding-based analysis. So these are all the issues, challenges related to coding. There are also challenges related to collaborations. First of all, many people need to collaborate in this context, and these people have very different backgrounds. So we think about people like Alice, who is a biologist, and we talk about Sally and Bob, who are bioinformaticians. And biologists, they are very knowledgeable about biology, but they might not be tech savvy in coding or setting up this infrastructure and doing debugging. Bioinformaticians, they're good at both biology and computation, but still their deeper understanding of setting up an infrastructure, how to parallelize some job, and even some advanced AI ML techniques, that's not their strength. And there are also some collaborations with people like my team who are from computer science. We are good at building systems. We are good at developing latest AI ML techniques, but our knowledge about biology, again, is limited. So how can we allow this kind of people with different backgrounds to work together in a very efficient way? That's one of the challenges. Even for the collaboration from different organizations, they also face some other barriers. Even within one lab, we often face a situation where some senior students, they write some code, they put the code on GitHub, and later the student has graduated, or even student has not graduated, a new student comes in, the new student wants to reuse what the senior student has developed, but that knowledge passing is really hard because it's much harder for a new student to read and understand the previous code. In many cases, a new student just abandons the old code and they will just start from scratch because it's much faster. But in this process, a lot of information is wasted. A lot of knowledge cannot be transferred to the new researchers. The same issue also exists for collaborations between different labs. If Alice wants to collaborate with another professor from a different lab, the challenge is even bigger. So talk about collaborations, there are already existing tools for that purpose. Here I list some of them, like GitHub, Google Drive, Dropbox, or even email attachment. These toolkits or services, they are good at some domains. Like GitHub is very good for managing source code. Even for our Texera code base is managed by GitHub. But GitHub, these kind of services have their own limitations for the scenario we are talking about. The main issue there is GitHub is managing source files. You can do version control, you can do git push pull, this kind of commands. But GitHub, these kind of services, they are not managing the runtime environment. If Sally has produced something and she pushes her code to GitHub, if another person like Bob wants to repeat what Sally did, Bob could download the data, the source code to his machine, but still Bob has to follow some README instruction to repeat everything Sally did. That process can be very tedious, can be error prone. So that process is very painful. Another limitation of GitHub is is mainly for programmers. As I said earlier, many people, they want to be part of the whole life cycle of data analysis, but they might not be very familiar with coding. And even for people like Sally, who is very good at coding, we want to make it even more efficient for them to do this kind of analysis. Now, here's the rise of AI ML, and we all know AI ML, they are getting extremely more important. And this domain in sequence analysis, biology, in all different scientific disciplines, we are seeing this great opportunity of the rising techniques of AI ML. But the question is, how do we utilize this kind of a state-of-the-art AI techniques? And many of these techniques require some advanced skills in let's say Python and R. And think about all the models available on some platforms like a Hugging Face, and these kind of models, they are not very easily usable by many people who have limited coding skills. So how can we make this kind of AI ML techniques available to the researchers in this community? That's one of the questions we have to answer. All right, I said many challenges. So what is our answer to those questions? So in the past 7 years, my team has been at UC Irvine, has been developing an open source system called Texera. The one sentence summary is it allows cloud computing services for sharing data and workflow-based analysis. So it has many benefits. Since it is a cloud service, people like Sally, they don't need to download any software. Everything can be done on the server through some browser. And it has many advanced features like a version control, share editing, share execution. And it has a very powerful parallel engine that can be capable of handling very large amounts of data. So this is a list of benefits. And these benefits might look very abstract. So the best way to show this thing is to give a live demo. So next, I'm going to, the whole thing is available on open source. Everybody can download it and install it. So this is one of the example workflows on the Texera platform. You will quickly see a live system that looks like this. And to illustrate all the benefits, so in next like 20, 30 minutes, we're going to show a live demo. So we're going to mimic the situation where we have Alice and we have two bioinformaticians. So in this demo, I'm pretending to be Sally, and I'm a bioinformatician. I need to do some analysis, but in a different way on the Texera platform. And meanwhile, we have another two co-presenters. One is my student Chris. He's also on the session. So he pretends to be Bob, and we have a real Sally from Cornell. She also in the session. So some of the questions that about biology, in case I cannot answer, Sally, the real Sally, will come in to answer those questions. So let's start the demo. So the way it works is Sally will come to this website, like the way we use Google Docs or Leaf. And the Sally can log in. Of course, for demonstration purposes, we have simplified the whole process. So Sally can log in by providing her username and password. And so after she logs in, she can see projects. So for this demo, we assume there is a project called single cell RNA analysis. This is the project we use to manage all our resources, like workflows. So under this project, if I click it, I see two workflows. You remember earlier, I showed a pipeline of multiple steps. The first step is running Cell Ranger. That one, let me click this one here. This is the first step. So this is embarrassingly simple because this is the step that wraps the Cell Ranger logic. This one is implemented using Python. Again, we do not need to go through the details of this Python code. What this operator does is to do exactly the same as what Cell Ranger does. to process large amounts of read data to produce count matrix. And since running this step can take a long time, can even longer in our webinar, so we for demonstration purposes, before this demo, we already ran this step to produce a count matrix. And plus, this count matrix is a much smaller scale to show the rest of the analysis. So next, I'm going to focus on the remaining steps from step 2 to step 7. So this is the second workflow. Again, we do not need to go through detail. At a high level, we are modeling the whole computation as a graph, or to be more precise, as a DAG. In this DAG, we have many different boxes, and each box we call it a operator. Sometimes people call it a node. For us, we call it operator. So each operator does one thing. And the edge between two operators shows how data can pass from the first operator to second operator. So intuitively, you can see data starts from here. It flows all the way through the edges to the end. In the middle, we also have branches like this one. For instance, this one is doing some visualization. So let me start the execution as I explain how this workflow works. So I click the run button. So at this moment, I have started the computation, and the color of each operator indicates the status of that operator. And the orange means that operator has started, waiting for instructions. And the computation happens from left to right. And to make this workflow runnable within our demo, we use a small data set. The whole computation of this workflow takes roughly 1 minute and 5 seconds. So the green color indicates the computation of that operator has finished. So at this moment, the first operator, which is part of the step 2, which creates a surrogate object, has finished. The green means it's done. Now this one is also green, means it's done. So this green operator is all finished. So this one is working, and now this one is working. All these guys are working. At this moment, I can show you some of the operators. So you can see this step, which adds some age data from different file, is written in the language R. This one, another step, is implemented using Python. So that's one of the benefits of the platform, because it allows different operators, different steps to be implemented in different languages. This is one of the barriers for collaborations, because some people prefer R, some people prefer Python, some people prefer Java. How can we allow people with different programming backgrounds to come together to work on the same task? So these 3 operators do the step 2, which does the cleaning of the count matrix. And then step 3 is do normalization. And step 4 does this dimensionality reduction. Step 5 is integrating data from multiple data sets from multiple donors. Step 6 is doing clustering. Step 7 is doing some annotation on the clusters. So let me show you some of the visualization results. So this branch is showing the result after this operator. So if I click it, I can visualize it. So this is a visualization chart. Again, this is the results on the sample data. When we run it on the entire data set, the results will look different. This one shows the results of after the step 4 dimensionality reduction. We can see it. Let's see how it looks like. So the x-axis is the principal components, and the y-axis is the standard deviation for each principal component. And this one is the cluster results. So we see the clusters, more like a UMAP. And then after this one here, we show the annotated UMAP, where each cluster has a label there. So basically what we did was to turn the original programs Sally wrote into this workflow. Now it's very visual, it's very easily understandable. The execution also very straightforward. So next, I want to show some advanced features related to collaborations. So let's imagine a case where this task is so complicated, Sally may reach her limit. And for demonstration purposes, I'm Sally. I'm going to introduce a bug in the whole pipeline. So I'm going to look at this operator, which is written in Python. So what this operator does is to really generate image to be visualized by this operator. So let me open this operator. So again, you do not need to understand the detail. It's just Python code. In this line, the Python code is retrieving one column using a key. So I just introduced a bug by changing this string object to some random characters, random string. So this is a bug, right? I sadly introduced for demonstration purposes. So now with this bug, I'm going to run it again. So as you can imagine, the execution will still continue from left to right, and it will take roughly 50 seconds for the computation to reach here. So you can see the timer here. So now it's 17 seconds. When it reaches 53rd second, the computation will reach here. And since we introduced a bug, and the computation will have some problem. And what I will do is, once it reaches that operator, the computation will pause to show something there and some message. And when it pauses, I'm going to invite my colleague, Chris, who pretends to be Bob, to help me fix that issue. So you can see at this moment, the computation paused because there is a bug. And the pink color indicates that each operator is in a pause state. The engine is also able to print an error message which says, hey, this X doesn't look right. Now, suppose Sally reached her limit. She doesn't know where the bug is. And what she could do is she can just even leave a comment here. Let's assume she can leave a comment here. I say, I think this operator has a bug, right? Something like this. So she can leave the node on this workflow, and this node can be passed to her collaborators. Now I'm going to invite Bob to join this session, to this workflow session, to help me debug this workflow. To do so, I go to this page. I can share this workflow with Bob using his email address. So here, Bob's email address, suppose is dkNET.org, right? Suppose that's Bob's email address. I give him the right access, and I click share. So at this moment, Bob should be able to receive an email notification telling him, hey, this workflow has been shared with you. So now, Bob, can you join the session and help me fix this bug?
Hello, this is Chris, and I am acting as Bob. So I will join the session now.
So now Bob joined, and as Sally, I can see his cursor. He's also working. We are currently working together on this workflow to fix it. And to see how Bob fixes the bug, what I'm going to do is I can click his icon, and I can click this one here. So what this one does is, from now on, I'm going to watch what Bob's doing there. I'm not typing anything. I'm not moving my mouse. Everything you're seeing right now is done by Bob. So please go ahead.
Okay, so first I'm going to click on the operator that is suspicious to have a bug. So I will click the operator. And then I'm going to look at the code content. So on the right panel, I will click on Edit Code Content. And I'm looking at the code, and it seems like in line 11, the tuple object doesn't have a field called X. So what I'm going to do is I'm going to change the field from X to object. now the issue should be solved.
So then, Bob, can you close this window and run this workflow again?
I'll run the workflow again.
Yeah, I think you need to stop the previous computation.
Okay.
Yeah. Okay. So now Bob has restarted the computation, and if everything works as expected in this new computation, again it happens from left to right. Um, everything should become green at the end after say roughly 1 minute and 5 seconds. So the first step, this one succeeded. Now the computation happens here, and it will reach this operator at around like 55 seconds. And if this one turns green, that means this fix has worked. And I think once this one turns green, it means the bug has been fixed. The rest should also be fine. So now if we see this, so this one is green, meaning it's running properly. The result, this computation branch, this branch has finished the computation. If I see the result, we should be able to see the visualization charts. The rest is still ongoing. So we are reaching here, everything is finished because everything is in green. If I click this one here, this is the annotated UMAP with all the clusters. So thank you, Bob. So you can leave the session. I can continue. So I want to pause here. So what I just showed is two people like Sally and Bob, they can work together on the same workflow, and they can work in this demo. Bob worked on the Python operator to fix that bug. During that session, if Sally wants, she can also go to a different operator, they are or any operator, and these two people can concurrently work on different pieces of this workflow. That's very similar to the way people use other services like Google Docs or Overleaf to work on the project. The difference here is in this context, a project is a data science job for sequence analysis. So before I continue, I would like to ask the audience if there are any questions regarding these features.
Yeah, there's one question from the audience in the chat. The question is, does it save the result of previous runs of the same pipeline? If so, can we differentiate them inside Texera?
Okay, a good question. The platform records all the metadata of each execution. I show you a demo. In fact, I will answer the question when I show the advanced features, and then this question will be answered automatically. So maybe I can continue the demonstration here. So on this canvas, we showed how multiple people can collaborate on the same workflow. We can use comments to pass knowledge. And this platform also has many other advanced features. For example, related to the question, the system keeps track of all the past versions of this workflow. Similar to many other virtual control systems, it is very valuable for the system to be able to allow people to go back to the past and see how this workflow evolved over time, and they can see differences. And the past history is very important. Related to the question, the platform also keep track of all the past executions. Here, we only keep track of the metadata of each execution, like what are metadata. For each execution, we show like who did it, who started the execution. You optionally can give a name. When did it start? When did it end? And whether it finished successful or it got killed, or for some other outcomes. And we also show some statistics of each execution. For instance, for the one we just did, if I click this button, we show we show some statistics about that execution. Again, you don't need to know the details. We show some numbers like for every operator, how long it took, what's the number of input tuples, what's the number of output tuples, and how many workers we use for that operator, that information is recorded on the server side. So these are the statistics for that particular execution. The platform also keeps track of all the past executions and can allow the user to visualize all the past executions. Here I show you some of the pie charts. So this pie chart shows for all the past executions who did these executions. So you see Bob did some, Sally did some, and the real Bob, Chris, did some. And this one is the status distribution of all the past executions. And also show the performance numbers like a histogram to show for all the executions what's the average running time. And we believe this kind of information is very valuable for people like Sally to know the history and use the history to gain more insight of the behavior of that workflow. So that's the version of the workflow history of the executions. And one more thing I didn't show, how this workflow is constructed. And we have a rich collection of what do we call operators. And each of the operators, the user can drag and drop the operator and leave it on the canvas. And then that's the way a user can develop a workflow. So these are all the features related to a particular workflow. So let's look at another case where after Sally and Bob have finished this workflow to do some analysis and they publish a paper. The paper gets accepted, everybody's happy. But people may ask, what if some other researchers from the community, they want to repeat what this lab has done? And the typical way to do so, as I said earlier, they can use GitHub. We know the limitations of GitHub. So on this platform, we want to make that publication of the analysis much easier. So Alice is a PI. Say Alice, she wants to publish this whole workflow. And one benefit of this workflow environment is Sally can share this workflow with Alice. Alice, she is expert in biology, but she might not know too much about coding. But still, for Alice, with her background, she can see this workflow very, very easily. She can understand it, and she can even run the workflow on a small data set for some other purposes, like for a presentation, because it's a workflow interface, not like a notebook interface. And let's say Alice or Sally want to publish this analysis and share it with the community. What she can do here is she can go to these projects, right? Projects. This is a project we started with, and all they need to do is there's a button next to this project, and if they click the button to make it a public, it means now this project is made public. Now it means other people, other users on the platform, they should be able to see this workflow, this project with multiple workflows. And what's more, other people on the platform, they can easily repeat the execution by going to the workflow and clicking the run button. And because the whole environment is on the platform, including the workflows, including all the data sets used by the workflows, they are all here. And the other collaborators from a different lab, from the community, they can just come here and do a few clicks. The whole computation can be repeated. So we can enable a scientific reproducibility very easily. And we strongly believe this is something our communities need very much. So let me use the remaining demo time to show a few other advanced features that can make the platform very easy to use, very friendly for many people. We saw the projects. For now, we have one project, but we can easily add more projects. We saw workflows. Let me show this data set tab. So the platform allows people to share not only workflows, but also data. Again, for demonstration purposes, we have pre-uploaded one data set called RNA data. This data, if I click it, it includes many files. And this data set only has a single file. But in general, a single data set on the platform can allow multiple files. In fact, it can even allow a tree of files with some arbitrary depths. And for this file, it's a FASTQ file. We can see some of the sample records. And if the user needs to modify this file, the platform supports version control, meaning for this particular data set, we already have 2 versions. If the user uploads or modifies some of the content or uploads a new file or adds one more file, and then we are still keeping the same data set, we produce just a different version. So now we can allow kind of a time travel. We can allow each user to specify a particular version of the data set. Then they can also make a scientific reproducibility much easier. So in addition to the feature of sharing workflows, this platform also allows the user, Sally here, to share also data set. To share data set, very easy. We can just click this button. Then we are making this data set public. Public means now other users on the platform can also see the data set. They can use the data set for their analysis. The quota tab shows some statistics about the usage, like because you can imagine behind the scene, a lot of resources about files, databases, computing resources. This quota shows how many resources each user has used. And we also support this feature called the forum. We want people to be able to have some discussions about all kinds of topics, similar to other platforms like Stack Overflow. So we have a built-in a forum feature. We have some advanced features for administrators. In this case, Sally is an admin, so she can see all the users. She can see all the executions, and she can also send some email to some users here on the platform. So everything can be done on the platform. So this is the end of the demo. I'm going to switch back to my deck to talk about other progress, other questions. So before I switch back to deck, any questions in general?
Yes, there is question from chat. So about reproducibility, how does Texera backend compares to GUIS or NIDDK? In other words, does it guarantee bitwise reproducibility of the project pipeline, especially with regard of dependency tree?
Okay. First of all, for some of the packages, I need to get familiar with them. I can tell you what Texera can do right now. And we also have some ongoing effort related to reproducibility. We definitely will look at some of the packages. What we do now is we just allow another person to run the same workflow on the same data set. We can make that process very easy. Now, if your computation is not deterministic, if you run it a second time, it will give different results. Then the collaborator can run in the same way, but the results might be different. That's because of the nature of the computation of the workflow. But we do have some ongoing effort about how to really do some logging to guarantee the exact reproducibility of execution. So that one is still ongoing. So we will look at some of the package you mentioned offline. There's one more question.
Yes, there is one more question. How are the computational resources managed and stored? If another lab wants to run the pipeline, do they have to adapt Texera to their own HPC core? Or would they subscribe to a space on the Texera server?
Okay, very good question. This is one of the questions my team has been talking about for a long time. First of all, computing resources are a big topic in this field. We all know some computation can be very expensive. So when we develop our platform, we are considering different scenarios. So one scenario is we want to set up our own on-premise cloud. So with the help of NIH, we are going to purchase some cluster of machines, and we're going to install the servers, set up this cloud Texera service, and then we're going to make this service available to the community. Like given our limited computing resources, we had to control our resources very carefully. Like one thing we plan to do is to give each user some quota like in terms of memory, storage, or or also cores, and then at least people can use the platform for their analysis. So this is one model we're considering. The second model we're considering is Texera is open source. We believe this open source position is a big advantage because many people, if they have their own computing resources, they have the freedom to download and install this whole software stack, and they can repeat exactly what I'm showing right now. But in that context, they can use their in-house computing servers and do their own management. We are very happy to provide all the support to guide them to set up the whole infrastructure. The third model we are considering is to leverage the public cloud, like with quite a few big providers like Amazon AWS, Google GCP, and Microsoft Azure. And we plan to support the model where some people can come to our platform and behind the scene, the computing resources are already allocated from, say, Amazon AWS. And then because AWS has almost unlimited resources, then the users can use our platform to do some analysis using Amazon services. Of course, in the second and third model, we had to work on the billing issues, like our resources could be limited. But that one is one of the open problems we're currently working on. Okay, so I'm going to continue the presentation to present all the other remaining slides. So I showed you the visualization results using the sample data. For the record, these are the results of running the analysis on the entire data set. I'm pretty sure people who are familiar with a sequence analysis, these figures look familiar to you. So this slide shows some statistics about the Texera platform. We started the development more than 7 years ago. We have a lot of active users, and we have a lot of projects, lot of users, projects, workflows, executions, versions, publication papers, servers. And in one of the largest deployments, we are running the whole platform on the cluster of 100 machines. Each machine has 4 cores. So that deployment has 400 cores. This is the number of files on GitHub. This is the number of lines of code on GitHub. And currently we have 7 active PhD students working on the project. We're going to get more. We have collaborated with at least 17 professors on different disciplines, including public health, bioinformatics, and criminology, social science. And we have a large body of undergrad students working on the platform. And 3 PhD students have graduated from this project, and 7+ years for the development. So there's one question in the chat window: could we rerun the specific pipeline from some specific step, but not to the whole pipeline after making some change for the specific step? A good question. So I didn't show it. The platform allows the user to run the workflow up to a particular operator. That one is already there. Now, if you want to start from a particular place, then if that place has been run before, has been cached, the system should allow the user to resume the computation from the cache operator without restarting from scratch. So basically, we allow the user to run part of the workflow as long as the part before the first operator has not changed. If that's changed, we have to start from scratch. Here's another example workflow we use to do analysis in a different domain. It's about brain image analysis. We have some ongoing collaboration with some faculty at UC Irvine, and they are analyzing gigabytes of mouse brain images. Not surprisingly, similar to sequence analysis, this kind of analysis is handling very large amounts of data. In this particular case, the data set was about 256 gigabytes. So we were able to run the whole analysis as a workflow on Texera. And this is the final output, which is a 3D model of some mouse brain. We are currently using the platform to do teaching as we speak. In particular, we offer a course. We're offering a course. The title is teaching data science and AI/ML using workflows. The class, we are targeting those non-STEM students because these students, they are not as tech savvy as CS students, but still they are eager to learn data science, AI/ML. In this deployment, we have like a cluster of Texera servers managed by Kubernetes, and we have more than 40 students. So this is the picture we took this week to show multiple people are accessing the server at the same time during the class. So there's a lot of workload on server side. The person who gives the presentation is one of our students, Yisong. So officially he's instructor of this class. We have another student, Chen. He's a TA of the class. This one shows a picture of some high school students who participated in a summer program last summer, and they used Texera to do some analysis on different domains. This is one of the workflows. So even for us, we were very impressed by the complexity of the workflow the team of these two students they were able to construct, and they got it very quickly. So it gives us the confidence that the platform is very easy to use for people with very little skills in coding, data science. They can learn it very quickly. That's why we're having a lot of efforts to utilize this system for education purposes. So one more question. Is it possible to specify the version of certain software tool in the pipeline? For instance, to see if certain version of YOLO can segment our images better compared to the older version. If I understand the question correctly, I think it's about whether we allow the user to have some control on some libraries like Python or R. I don't know what language YOLO is implemented in, whether the user can control the libraries or versions of libraries on the platform. This is one of the tasks we are working on. We do have one student actively working on this topic, and the solution we want to develop is based on the notion called environment. So whenever we have workflow, we also need to provide something called an environment. In the environment, we can specify, say, the data sets you want to use and the computing class you want to use. And for libraries, we want the user to be able to specify the libraries or even the versions of libraries. So that one is ongoing. And our answer to the question will be yes down the road. So we're very happy to announce together with other colleagues, we are receiving a new NIH award managed by the dkNET organization. So together with other colleagues from UC San Diego, UCLA, and Cornell, and our vision is to serve the research communities of diabetes, endocrinology, and metabolic diseases through the fair sharing of data and knowledge. I hope from this demo you can see on the platform, researchers can easily share their data, their analysis, they can collaborate, and we want to use this platform to achieve this goal. As part of this project, the dkNET award, we have a pilot project. This one is on the dkNET.org website. So I showed many advanced features of the platform, and we are currently inviting some users from the community who are interested in this kind of platform. Due to one of the reasons mentioned earlier, since the computing resources are limited, we cannot open the whole service to everybody. But we want to invite some people who see the value of the platform, who want to use the system to do some analysis or publish their research results with the community. So if you're interested, you're welcome to contact me or contact Ko-Wei, and we can work out the details of how to get you on board. I mentioned many very powerful features. Now, here I'm showing you some of the open questions. Since our time is limited, I'll just go through them very quickly. We can use remaining few minutes to answer more questions. How to support an interface similar to ChatGPT to make the whole process much more user-friendly. How to provide more operators and workflows related to sequence analysis. And how to make some of the steps as operators configurable by allowing people to modify the operators or parameters. Some of the steps are computational bottlenecks, how to parallelize them, like Cell Ranger, or the other one is called a Star Solo. How to make existing AI ML techniques easily available to the community. How to make the process of migrating some existing programs to workflows very easy, automatic or semi-automatic. How to support public clouds like AWS GCP. So the list will go on. So we have many open issues that need to be solved to achieve our goal. So to summarize, Texera is an open source system that supports cloud-based computing platforms to allow very powerful collaboration, sharing of data and analysis. So, and this platform can make it easy for people to do collaborations, can make latest AI ML techniques more easily available to the community. And we want to use the system to make scientific research and collaboration much more efficient. So this is the last slide. So I want to thank all the people who have helped me prepare the presentation, also develop the whole system, including some people from UC Irvine, also some colleagues from Cornell, and the entire Texera team at the UC Irvine. And the work is supported by NSF and NIH. So thank you.
Okay, thank you, Dr. Chen Li's fantastic presentation. If you have any question, you can unmute yourself to ask question right now. It's our Q&A session. We have a few minutes left, so please feel free type your question or ask question. Dr. Mahmoodian, yeah.
So I have a general question that kind of covers two of my previous questions. Your workers, how are they constructed, basically? I'm asking this because, of course, as a bioinformatician, there are tons of pipelines that either I wrote myself or other people have written already. And that was one of your open questions as well, like how to kind of import the existing pipelines into Texera.
Yeah.
But I'm still kind of puzzled on how each of the workers are constructed. Is it something based on, for example, Slurm jobs, or is it something that is a virtual machine that is constructed on the spot? Thank you.
Yeah, it's a very technical question, but thank you for asking. So I can give you a little bit details about how we parallelize the computation. So we are now using Slurm, short answer. We have our own way to running a job on a cluster. Behind the scene, our engine called Amber is built on top of another engine, which is an actor model-based engine. The name of the engine is called AKA, AKKA. It's a Java-based actor model-based parallel engine that can run on the cluster. So we run the AKA engine to manage the computing resources, but it is our job, Texera's job, to decide how many workers we can allocate to each operator. So that's one of the open issues we are currently working on, which is how to smartly decide how many workers I should give to one operator. This is ongoing.
is one from the chat for the direct message. So as a bioinformatician, do I need to publish paper before share my workflow using this platform? How do people cite my workflow or data?
Whether you want to publish it on publish workflow before you publish paper, that's totally your decision, right? So we don't have any like authority to decide what you should do related to your publication. Now, regarding whether you can cite this particular link of the workflow, our vision is as the system is getting more adopted, it becomes more available to the community, we can standardize the service, and then we can provide a unique ID, and that ID could be part of your even your publication. You can cite that one. And of course, that decision assumes the platform is adopted by the community, and we have the resources to provide the services kind of forever, right? So that one needs a lot of other discussions.